Well, welcome to the Structural Modeling November 2017 video conference. Today we're talking about the Technical Report 14, the Interconnection Matrix, and some ways to address issues with implementing software tools and processes to create matrices that are associated with interpretive structural modeling and basic structural modeling and just structural modeling in general. So with that, what I think I'll do is ask if anyone has any questions about the report. We sent this out a couple weeks ago. If there's anything they'd like to have highlighted as we go through this, any burning questions that we'd like to have addressed. And then after that, then I think I'll just kind of walk through the report for a while. So are there any special things people would like to have covered?
Not in particular, Joe. Maybe as we progress, I might have some questions.
Okay, so there we go. Well, then go ahead and you don't have me going in now. Then just go ahead and feel free to note your questions or break in their burning topics, and we'll talk about them at that time. Okay. So essentially, in structural modeling, really one of the key benefits of structural modeling is its ability to effectively engage very large-scale systems. And it does this by using inference, so that you get some information. You spend some resources, you get some empirical information, you take that information, and then you use that information using mathematical inference to get a better insight into your system structure. And so you incrementally build your insight into the system, and it's kind of like the scientific method. So you do some empirical work, you think about what's going on, you do some inference, you do some logic, and then you decide what is the next set of empirical work I'm going to do. What am I going to spend my resources on? Exactly how am I going to, what are my next steps? And so in the interpretive structural modeling, most of the software has gone through and said, okay, we will have a situation where the computer will tell you which is the next item to give us empirical information on, which is okay. And then the group works on that, develops the answer, gives the answer back, goes into the computer inference, and then the computer asks the next question. At this and going through it, that's very efficient because you can reduce the number of questions and therefore the resources necessary to create a system structure in certain cases. And so that's what we're talking about today, is actually how do you start this process and how does it go forward? And so basically we'll talk about first we need to talk about what the process is. And Warfield defined the process as transitive embedding, which is a process in which intellectual technology is employed to convert a set of collective perceptions to a matrix model of the structure of a system. So we take a group of people that have collective perceptions and we create a model of that system of perception. And this model is founded on a particular, relevant, transitive, contextual relation, okay? So notice here that that Warfield said it was transitive, and they said it was particular relevant, right? And so what we're looking at now is saying, well, what are the characteristics of a particular relevant contextual relation? This implies that there's some contextual relations that are not relevant and won't be good to be used here. This represents an intermediate product in a larger process aimed at developing insight into complex systems through the development of interpretive structural models. So what we're looking at now basically is, is there a characteristic of a contextual relation, natural language relationship, that makes it good to use in these cases? And so that's basically what we're asking here is, are there some that are allowed and there's some that are not allowed? And we go through and look at this. And of course, the reachability matrices, I assume everyone's is familiar with the reachability matrix and how it works within the structural modeling process. It has a number of roles that it plays and gives you different types of information. It's kind of a matrix model, or a model matrix for the matrix model of antecedent that precedes. So it's a fundamental type of approach. And so here's the first matrix example that we took from the literature to look at. This is from the Structuring Complex Systems and monograph from Battelle. These are fairly rare monographs. You can get them. If you're interested in this area, I would suggest that you try to get them. They're very interesting, and they're a little bit different. They're the work that was done, which the societal systems and the mathematics of structure were all based on the Battelle monograph. But if you look at this matrix, we notice some things about it. We notice there's a lot of zeros in the upper triangular, but we have some ones up there. Some ones up there. And you say, okay, we have the lower triangular, so okay, we have a lot of ones, but we have some zeros down here. And this then basically indicates that this is an unordered matrix, and so that it needs to be ordered or structured. And primary indication is the ones in the upper triangular. And so we go through this, and this is the graph of the matrix that was prepared by, well, this is the structured graph that's associated with the matrix we just looked at. And it's shown here, there's multiple structural threads through this graph. We have one here in red or orange. It goes from 14 to 10 to 6 to 2. That's a pathway through the graph. Another one here in green goes from 11 to 7 to 3 to 9 to 1. And of course, you can always envision other ones like 12, 7, 3, 9, 5, 2. So there's multiple structural pathways through this graphic, which basically is an indicator that that it's a local type of relationship, and we'll talk about that a little bit. It's one of the things that we really need to develop and put together. But in the same monograph, right? Well, no, this one actually adapted this one from Planning and Policy from the Societal Systems, but I think this was also in a monograph. You can see here the implication matrices for the transitive embedding component. We have the upper triangular area here. This is filled with inferred zeros, right? Filled with inferred zeros, this whole area. And then over here, this is filled with inferred zeros. And these components here basically are the width and height for the ones here, or the in this particular case. So this is 1, 2, 3, 1, 2, 3. And this particular size here, it's a square matrix, so it's the square of the number of zeros that are below the intersection. So this is pretty straightforward type of geometric analysis of what's going on. But besides the inferred ones that are up here, I mean inferred zeros that are in blue, right? We have inferred ones, right? So we have yellow, all inferred ones. And so this inference is the appears to be the place where the power for reducing the number of empirical decisions and the amount of empirical information needs to be collected is here. So we went through and started looking at this a little bit, see how that worked with our other matrices. So the matrices that we started out with at first, right? We said, well, let's just pick at random an object, because that's the way you start with the scanning method. You don't really know anything. You know you have these objects, but that's it. You have to, what's the first thing that you do? Well, the first thing you do, you arbitrarily pick an object. So that's what we did. We arbitrarily picked 5. And then we started looking at, well, okay, actually in the matrix above, we actually know what the initial conditions are. So let's see how that works. And if you're starting with a unknown scenario, you wouldn't know what the initial conditions are. So here's what we're doing, is we're kind of thinking about this method using something that we know the initial conditions, and then we start mapping it. So if we pick 5, then the areas that are circled in red, we're saying, well, I think we have an error here in inference, because we've got 1s up here, which we know are there, but the inference says that should be 0. And of course, the same with where you're supposed to infer 1s. So that's kind of an indication that we might have some issues right off the bat, just with starting the scanning method. And then we said, okay, well, let's look at it again a little bit more. So we arbitrarily pick object 6, right? And again, we arbitrarily pick object 6. And again, we have the red circles, which indicate probably an error in inference. And this error in inference, what it's doing is it's smoothing the, appears to be smoothing the structure into a single thread. And as we showed earlier, there's multiple threads through this particular structural system. Okay, come on, guys. Well, my chart doesn't seem to be moving here. Okay. Let's try it again. I moved it up here, but it's not moving on the screen. So I'm going to have to stop screen sharing and try it again. Hopefully everyone's there. You can hear this. Come on, guys.
That's okay. And it was moving, Joe.
Oh, it was moving. You could see it moving?
Yes.
Do you have the blue on there, or do you have just the white?
White. I mean, I can see the paper going up and down, yes.
This must be my screen that's frozen. Okay, that's good. All right, so now here we have the rearrangement. Now we have the ordered matrix, right? Now the ordered matrix of this.
We don't have it open.
What, dear?
It's not quite up yet. Are you screen sharing again?
It was showing before, but now it's not when you stopped.
Okay, it was showing before, now it's not. Okay, so let's see. Okay, let me try it again. Okay, so here we're going to go. We'll try this, share this.
It's up.
What do you see?
We see adapted from figure 2.8.
Okay. All right, good, because that's not what I see, but I'll go with that. Okay. I'll just work on the other screen. Okay. So we've got Warfield's figure 2.8, where the matrix is rearranged here. And one of the things that we see right off the bat is all of the upper triangular is zeros. Okay? This is, I think, is important. Because it indicates that This is an asymmetric relationship, and we can use that for certain types of inference and for certain things and that. But so the upper triangular being zeros is good.
What you're showing is a 1 to 3.
Okay, so okay, well, this is what I have here. Okay, so and we can see that the upper triangle, except for we just pointed out these two that are symmetric, right? This one and this one are symmetric, and this one and this one are symmetric. Those in our analysis process would collapse into one node, and then after they collapse into one node, the upper triangular component would be all zeros.
So, Joe, in this one, then what you are showing are either both series and parallel processes, right? Just unidirectional. That's all that we'll be looking at here, right? Or tensor relationships. Is that what this matrix is showing?
Yeah. So what this matrix shows, right? Let's just use the natural language relationship connected to, okay? Because we haven't really assigned a natural language relationship. So if we say that object 2, right, is connected to object 5, object 2 is connected to object 6. So this being a reachability matrix, it says that there's a pathway between these using connected to. Here it says that 8, right? 8 is connected to 3, and here it says 3 is connected to 8. So that is a symmetric connection. And here it's 4 is connected to 9, and 9 is connected to 4, and that's a symmetric connection.
Correct.
The symmetric connection would be reduced to a single unit, to a single node, and then everything in the upper triangular would be zero. That makes sense?
Yes, thank you.
Okay, so that's just kind of, but we see below here that we have these zeros, right? And these zeros mean there's no connection between these, and there's no structural thread connection. And we see that there's multiple pathway threads through the system, right? Either to 2 or 1. But there are also areas where there's no connection. So that's a type of scenario where we believe the local attribute is weaker in inference than with the global type of attribute, which would have all ones. Global attribute would have all ones in the lower triangular and all zeros in the upper triangular. Okay. And so what we've done now is from the literature, we've gone and looked at, should be looking at Warfield's problem 2 digraph figure 1016. And so this is significantly aggravates. And we adapted this from, again, the Science of Generic Design, one of the examples there. And again, we show multiple threads. You know, it's this orange thread, 8, 9, 9 to 7, 7 to 2, 2 to 1, 6 to 5, 5 to 4, and 4 to 3. And then, of course, there's this interesting crossover here at the 2 top nodes. When we look at this graphic, we go through and we look at it. So we look at the matrix of this diagram, and we see that we have some ones in the upper triangular here, but they're not. We don't appear to have any symmetric ones. We don't have any symmetric connections across here. Right? It's all kind of clean, but we have zeros in the lower. Right? We've got some ones in the upper and zeros in the lower. Okay. So then we start doing this again. And we say, okay, we'll do this process. Again, we say, well, we believe we have errors here. Here, these really a type of indicates an error in this process. And then we'll go and look at, we pick object 6. Object 6 is interesting because it doesn't infer anything in the lower at all, but it does correctly infer all the zeros in the top. So you'll see that it's kind of an interconnector, really has only one connection. So the multi-threaded graphs are a little more involved. And so then again, we'll arbitrarily pick 7 here. Again, we believe we have errors here, 3 errors. So what we have found is, or what we think is necessary, is we've actually identified 2 different groups of natural language relationships, 2 basically different kinds for this activity, which are the natural language relationships that are global in nature and have a mediating global artifact that's used to structure these objects. And then the local natural language relationships that do not have a global mediating artifact to structure their relationships. For example, here we have the is north of natural language relationship, which is a geometry type of relationship. This is from the 19 cities problem, and it's 19 cities are all ordered here. And you can see that the lower triangular is all 1s, and the upper triangular is all 0s. A key takeaway from just looking at the graphics and looking at the matrices is that once you've ordered either a global relationship or single-threaded or a local relationship which is multi-threaded, either single-threaded or multi-threaded, right? You have all 0s in the upper triangle. That's, I think, an important observation that can be used to increase the efficiency of certain types of more involved inference techniques. We'll need to have probably some different types of logic involved when we start addressing the local relationships in more detail, but we'll see as that goes forward how that works out. We have, of course, the structuring relationship classes. We developed this last month where we talked about the 5 different classes. And so we can start separating these out now between global and local. And of course, a cluster is neither, right? And so we have this cluster, basically, which is a network. And it's neither global nor local because it's symmetric. And so we basically, the way we're looking at this right now is basically have these 5 big buckets of natural language relationships that we can use to address this. Okay. So, just looking at basic structure and how it works, and then so you start mapping these classes to groups of matrices and structural graphics, and then you can map those interactions to groups of natural language prose. And in this way, what we're doing basically is taking the 3 system isomorphic forms, prose, structured graphics, and mathematics, the matrices, and making them equal. So they're isomorphic. They mean the same thing, right? And using these 3 forms, we now are able to start identifying the key characteristics that motivate the logic. And it's important to use all three forms so you can identify the criteria. It's very difficult just using prose to understand the difference between global and local. But when you map it to a structured graphic or you map it to a matrix, very, very clear when you look at those forms, which is global and which is local. So the scanning method, we went through and looked at that, and basically it's important, but we couldn't, I've never been able to figure out how to do it as it was presented in the literature. That's not saying the literature is wrong, I'm just saying I never could figure it out. So I created a different approach, and a different approach is probably, we'll go back up here and I'll just find one of these, find the basic one and just explain what I did so that there may be clearer approach that Mary and I use. So right here, right, on this one in the transitive embedding piece, I never could figure out if these all had to be ones or not, right? And the zeros here and the ones here. So in many realistic cases, these are not grouped. In multi-threaded cases, they're definitely not grouped. Single-threaded cases, sometimes are grouped. So the primary difference in what I did was I just said, okay, I'm not going to randomly select objects. I'm not going to do that. What I'm going to do is I'm going to very stepwise in a structured fashion, I'm going to start up here in this corner, and I'm going to take the first one and the second one, and I'm going to compare them and order them. And then the second, the third, and the fourth. So I start at the top. I don't randomly select. I come down one at a time, and I start ordering these objects. And in doing that, I create two basic parts of the matrix. So the top piece is ordered, and the bottom piece is unordered. And I incrementally order this matrix from the top to the bottom. And so when I get done, I have a completely ordered matrix, but I'm doing it one at a time. And so let's say I have 5 of these that are ordered. I take the next one. Well, I take the next one, I have to figure out where it fits, or if it fits in the ordered piece, right? Where it fits in the ordered piece. And because this part of the matrix is ordered, then I can use standard computer science and mathematical algorithms like binary trees and binary search to actually efficiently place that object in the ordered section. So I started at the top and I just started ordering. I didn't do random picks because it wasn't clear to me all the permutations of the types of things I was running into when in real matrices. But they weren't, a lot of them weren't clean like this. So I just started at the top, I just ordered it all the way to the bottom. Then in the ordered section, I used standard computer science algorithms to increase the efficiency. And that's one area where, you could use some detailed research on that to see actually how efficient that is. Okay, so let's do this part. All right, there's key visual, key understanding here is that, both global and local, when they're ordered, have all zeros in the upper triangle. That's a key structural feature. Clusters are the kind of way we go through and look at this, segregate them, and start assigning characteristics so we can pick the best approach. When we talk about the scanning method, it said here we were basically been unable to effectively implement. So we've done different implementations. This code's available on GitHub, on the web. We'll be talking about that more. Next month's report, we'll talk about what's available, kind of a little bit how it works, the things that we are going to change as we go forward now and develop our next set of open source software. Which relationship types are important? Well, we now identified two classes of natural language relationship, global and local. With these concepts, now we can have a more precise discussion of structural modeling and the types of tools that need to be applied where. And I think that's one of the more frustrating things in the past is that really didn't have that level of conceptual formulation so that we could start discussing these things at this level of detail. So basically, what it says is we talked about the scanning method and the coupling method, and we developed the ART, the abstract relation type, and also the AMEI, the model exchange isomorphism, to look at these things and how we developed these 5 categories. And so these things are becoming more well-defined using the 3 isomorphic language forms that reinforce each other. And it says we now have turned our efforts to open source architecture and software, and we'll be working on that. So with that, I'm going to open it up for questions, comments. Aha!
You stunned us, Joe.
I've stunned you. How have I done that?
No. Let me see if I can see if I understood. So basically, what you're exploring right now is the capability of what Warfield did. I mean, an original software, identify some limitations, and you're going to then derive better algorithms so they can handle more structures, right? Is that part of what you're looking into?
Yeah, I wouldn't say they're better algorithms. What I'm saying, so we go all the way back to the front, right? We go all the way back to the front when we talk about transitive embedding, right? And say what Warfield said was it was a specific type, of relation, specific kind, right? Had to be transitive, but it also had to have other characteristics, and that wasn't well defined, right? I've never seen that well defined. Let's go back to the front here. Now, can you see this, a process, right? Process in which intellectual technology to convert a set of collective perceptions to a matrix model of the structure of the system. This model is founded on a particular relevant and transitive contextual relation. The contextual relation is the natural language relationship. Everyone focuses on this part. Oh, it's got to be transitive. Okay? Yeah, okay. Has to be transitive. No one focuses on this part. Particular relevant. How do we talk about ones that are relevant and ones that are not? So it appears to me for Warfield's approach, right, that the particular relevant has to do with a global characteristic. And before we did this specific activity on this report, I went back through the published literature in the science of generic design, and only about 3 or 4% of the published events, structural modeling events that were in that book, used local relationships, okay? And I'm not sure that those were actually hosted by Warfield. So if I look at this, there's some strong indications that Warfield worked with global type of natural language relationships, which are particular relevant that he's talking about, but he didn't define what it is. What are the characteristics of a particular relevant contextual relation? Okay. Then when, let's see, George Clear, right, invited Warfield to write his autobiography, right? And if you read that, one of the things that jumps out at me anyway when I was doing this work is that Warfield is very, very clear that Christakis was the person that invented and championed the use of aggravates. And aggravates is a local relationship, right? And so I'm not saying that that you can't develop structural modeling software techniques and processes to effectively address natural language relationships that have a local attribute. However, I think that they're going to be different than the ones that you're going to use on the ones that have a global attribute. And this distinction, I don't think, has been made in the past. There's been a lot of confusion. And as I said, when we first started this activity with Kevin, I was hoping Kevin would make it today. But we started with Kevin on this, is basically he said, well, look, we need an open source test bed so people with different softwares can, closed source softwares can actually have something to test so we can see how it works, right? And so that's kind of how we started down this path, and that's kind of how we got here. Does that make sense?
Yes, it does. Thank you, Joe.
Yeah.
Joe, can you picked up on these 19 cities. Can you say something or point me to the paper that refers to the 19 cities that you're using for your matrix?
The 19 cities problem? Yeah, okay.
Yeah.
That was kind of a little bit glossed over. So I think the best way to do that is to go ahead and bring up another screen here, and I'll show you the resources on that. The 19 cities problem was basically the first problem that we used when we transitioned from the abstract analysis using the SAGE math tools from the University of Washington to the JavaScript types of applications. So I wrote a Java. Well, first of all, I did the 19 cities problem in a spreadsheet, and I worked it all through a spreadsheet and did slides and put those out. And then after I did that, worked through all the logic on that, then I did the JavaScript. So I'm going to just go ahead and try to show this other screen and show you where the resources are on the 19 cities problem, because it's kind of really one of our basic examples that we use. Okay, I'm over here. Let me try to get over here. Oh, my application screen. I'm going to go with this guy. Yeah. All right. So, can you tell me what you see?
See your website. Please? Your website. Systems Concepts, Solution to Complex Problems, featured presentation.
Okay. So good. So if we go down here on this one, so here is the basic structural modeling project. That's the one we did first, and that's when we went through and did the the work with the SAGE tool. We have videos on YouTube, what they are, and then structural modeling series. And I also have these original slides, right, that are there for download. I have a link to the Sage Math tool here. And these all are based on the 19 cities problem. So this is kind of the fundamental work that we did. And then, and now the materials in the GitHub at this particular, we have, let's see if that link, that's not coming through. So I do have the material on GitHub, and I'll go ahead and send out that material, links to all that later. But that's the 19 cities problem. That's the one that we developed in depth. There's a lot of information on it. Got videos, got charts.
Did you write a paper describing what the 19, or is there like a reference where the 19 cities problem is described? Or is it like, I mean, I guess, because I came into this just after you started all this, like about probably, you know, some late 2015. So I missed this background piece.
Sure.
And I need to go back.
Okay, so let's check that. I think there is. I'm just trying to think of the best way to look at that. And I'm going to say probably we're going to go to ResearchGate. And let's see. Attributions. Just looking it up here. I think we did some papers for the in COSI 2015 in Bellevue, and we did a tutorial there. I think those series of papers, I think we did 3 papers and a tutorial there. I think those are the background on this 19 city problem, and I'll send those links out.
Well, that's helpful. After. I mean, I came into this conversation in late 2015, early 2016, so I'm missed that.
Well, if you have, I'll send that out. If anyone has any questions on how that is and how it works, and let me know. There's a lot of material there, a lot of videos, a lot of charts and so forth. But I go through it step by step of how it works. In those particular. So let's see. What's on your screen? Oh, screen sharing. It says, I'm going to stop screen sharing. All right.
Nothing.
Can someone tell me what?
Your picture.
You see?
Just your picture with little circles every time you talk.
Okay. Now let's see if I can go ahead and share again. Application window. Go here. All right. So I should be back to the document now. There you go. Okay.
We are back. We are back to the document, but Joe, this system structuring framework, or I'm sorry, structural modeling framework in 2015 is where a lot of that information on the 19 cities problem is. So
okay, yeah, and so I'll prepare a kind of a reference list for the 19 cities problem, send it out, and kind of annotate that a little bit so you know what information is where. Mitch, please. Okay, let's see. We've got a jump coming in, but. All right, so I'm gonna try to invite Jack because he just sent a note that I saw. And okay, so we'll see how that goes. All right, are there any other questions? Well, in that case, what I think I'll do is kind of describe what our future plans are.
Joe, I have a dumb question, and I'm trying to catch up, looking back in my notes, and I'm sorry I didn't read your piece in advance this time. Did you send it out to us?
I did.
You did. Okay. Well, we didn't get that for some reason, but I'm trying to remember what global versus local is, and you probably actually just covered it today, but I've been trying to search back in my notes, and so I'm disoriented. So if you could, again, carefully go over global and local, I'd appreciate it.
Okay, so the concept of a global relationship is a mediating artifact between two interacting objects. So, for example, gravity, right? We have a global gravity field. When I say one object is heavier than another object, that statement, that relationship is mediated by the global gravity field. When I think about geometry, right? Because of the way that human beings live and move around, we have this global concept or artifact of positioning, right? So that's global. Local is it two objects interact.
Hold on a second, Jack. Jack, can you turn your microphone off, please?
Yeah, so we have two objects interacting without the mediation of a global artifact. So they just interact with each other without any mediation. Does that make sense?
Can you give an example like you did for the...
Oh, I think an example of local would be aggravates. Object A aggravates object B, right? Object B may or may not aggravate object C, but object A may. So when you have a local relationship like aggravates, you're just considering the interaction of two objects.
Question.
Sure. Hi, Jack.
If A aggravates B and A aggravates C, does that make aggravate global?
No.
So
I was going to ask, what's the relationship between the global-local distinction and the cases of transitivity?
Ah, excellent. Okay. So global and local are independent of the logical properties, right? So we have what we're talking about. Remember, we're talking about relative aspects, right? We wanted to have, want to be able to identify a relevant contextual relationship. And so we've got the logical property groups, right? And we have the global and local, and they're different. And that's really a good question, Janet, and it's what I'm addressing it pretty much in detail in the next report, because I'm going through and now describing these characteristics, and then what type of software or conceptual approaches you need to have to analyze it. So I would say right now that if I have a hierarchy that's single-threaded, which is global, and a hierarchy that is multi-threaded, which is local, the same set of logical properties. But as I said, I'm going into that in more detail for next month. And I apologize if you didn't get the pointer to this month.
Yeah, did you send it out to the list or just us?
Oh yeah, I sent it out. I sent it out to the list a couple times.
Oh really?
Sent it out on a pointer out on the out on the calendar notes. Also had a pointer to it. So about 3 times. But you can always, they'll always be posted on ResearchGate. And so you just go to my ResearchGate thing there and look for it. They're all there.
Okay. Yeah, usually we do get them, get the links a few times, and this time we didn't. Okay, good. I guess I'd also gotten confused between, do we have a Google Groups page as well for this project?
Well, depends, I guess, on what you mean by Google Groups. They have a group email list.
Okay. Okay, so we don't have a separate site where you're collecting things. So it's ResearchGate. It used to be your website, and now it's ResearchGate that you're using as the repository?
I think what I'll do, because I have a number of these now, is I will detail that and send it out. So I have my ResearchGate site where I publish the research that Mary and I are doing.
Mm-hmm.
And then I have 2 websites now, my old one that I've had forever. And then I've started a new one, and actually I've started 2 new ones. So I'm going to be developing those and bringing those online. I have a GitHub account where I am doing the software, put all the software up there.
Right.
And I'm getting ready to initiate and deploy a GitLab account for community work on this software if there's people that understand that and would like to do it. So
yeah, if you could put a key at the top of your systems concepts site of all relevant other websites, that would help.
Okay, just give
yeah, I do see that you sent it out to the list. I guess that was so long ago that it had gotten bumped down. Okay, very good.
Okay, I'll do that. I'll also, I'll send it out an email. Pointers list on the systems concept site. Okay. We've got about another 8 minutes left. So let's see. Any other comments, questions? All right. In that case, I'll kind of go ahead and give a little bit of an overview of what we're going to do next. I've talked about what we've done with Sage software. It's on GitHub. And the JavaScript web apps that are on GitHub. And the JavaScript web apps, very old style JavaScript that I just hacked together to get something out there to show people how things work. We're going to re-architect that set of JavaScript. First thing we're going to do is create a more robust mathematics, a binary mathematics library in JavaScript I can use in any environment. What I'm using now and those other ones are statically kind of bound into them. And then the next thing I'm going to do is using the new JavaScript version is I'm going to modularize everything, make it into modules, and it will allow us to have recombine and use different parts. And as you can see, we have kind of like 5 categories of things we're looking at now. And we can, having these recombinable, reusable open source objects, then that will allow us to reuse and the code in a much more efficient way. And especially if other people want to use it, they want to just use the library and not use their, make their own front end or whatever. So there's basically break it up into parts, open source, look at it, and it'll be more, much more usable that way. So that is looking at probably 3 probably looking at 5 different web applications, and you would select those. Now those would, for more advanced systems, would probably string those together in certain ways, and you allow those to perform certain functions. In this particular case, we're going to just develop these 5, modularize them, and let them set. Then next, after that, we might be looking at a microservices type of architecture that would allow multiple concurrent evaluations through different steps. But that's just kind of where we are now, and I'll be in the next report going to detail the current state of the software we have out there now, what information's out there, and what we're planning on doing next. And so there's going to be technical improvements, changing from static namespaces to reproducible, distributable libraries using JavaScript version 6, and also adding new concepts and adding whole new areas. The 2 pieces are going to be the multi-threaded ones. And those multi-threaded ones are going to be interesting because I think they're going to be more involved with adding some types of local rule sets, some local artificial intelligence and knowledge-based things. I'm not quite sure what that's going to look like, but it'll be fun to develop it and talk about it.
I do have a question. So the multi-threaded, is the threads correspond to the local relationships? Is that right?
Yeah. So a global relationship has a single thread.
Okay. Okay.
A local relationship can have multiple threads.
Uh-huh.
A local relationship can also be single-threaded, but not usually.
Okay. And what about the relationship between Warfield's use of the word context and this notion of local and threads?
Right. So the threads are a term that we've used to describe the structure of the structured graph. And so when we have the 3 forms of language, prose, structured graphics, mathematics, threads basically talk about the form of a structured graph. So when you see a system in a structured graph, you can look at the threads through it. It either has 1 thread or multiple threads.
Right.
Didn't use that. The idea of global and local was not developed by Warfield. However, it's my impression that he used global relationships and that other people used local relationships. And as I said, he pointed out in his autobiography that Christakis was the one that pioneered the use of aggravates, which is a local relationship. So, and I think that's where kind of a key discriminator here. So we need to develop the language, develop the concepts, and then we know which type of inference to apply in which case, and then we can start making some progress.
That's very helpful. And then his use of the word context, was that on the ISM side for the group?
Relationship. He talked, yeah, that was in structural modeling, the whole idea of structural modeling. So the idea was that you needed to have a context to facilitate the application of the proper basic structural modeling techniques to the ISM. And so Mary and I developed the structural integration modeling piece to fit in there to talk about that.
Right.
All this stuff that we've developed and started these concepts to deal with, you know, it was, I assume it was just known to him. You know, it was just
right.
Obvious this is the way it works.
Right. Yeah.
But we need to have different words to talk about.
Right. It was in his context. Right.
Exactly. He didn't. That's it. Well, there you go.
Right.
Well, okay. With that, it's gonna. So who's doing
Well, I guess it partly depends on if Kevin is coming back in, because he always has good stuff to
Got a note
talk
from Kevin. He's spending 3 months in Cyprus. We
Uh-huh.
expected him to be here, but maybe he's traveling there. He had a medical condition
Uh-huh.
that might have impacted his travel.
Right.
I guess I'll.
Okay. I guess at a minimum, it would be interesting to discuss, since Jack and I, and maybe Tom will join us, are going to be promoting this track for the Ontology Summit in the
Okay.
spring, relating context to ontology to systems realization. And it would be very interesting to hear about Warfield's understanding of context, and it'd be great to have a conversation about that, whether we have a presentation on it or not. So if Jack, if you're available, and Joe and Mary, maybe we can plan to have a discussion on that in 2 weeks.
Sounds good. I'll put it out.
Great.
Well, thanks, everyone.
Joe?
Yes, Jack.
Sorry. Is there some place that I can see your ontology?
Jack, I tell you what, I don't even see my ontology except maybe really late at night, after I've been sleepless. No, that's really a good question, and it's fragmented, of course, because what I'm doing is I'm constraining my ontology by the languages that can represent that ontology.
Yeah.
And I'm requiring that what I'm talking about now has to be isomorphic across 3 forms.
Yeah.
Right? So that greatly constrains it. So,
well, my problem is that I think that your work is really important, and that somewhere around 1 million people who are screwing up systems would benefit from understanding what you and Mary are doing. But I have not been able to find a way to get that dialogue started.
Right. Well, one of the reasons we started the second meeting in the middle of the month was to discuss questions of ontology related to what Mary and Joe are doing. And Kevin has done more work specifically on that question. So the second meeting is more ontology focused, though it's an open-ended exploration. It's not there isn't a particular ontology at this point, but we're looking at those questions. So context ontology and Warfield's approach, is a great topic for 2 weeks from now.
All right then. With that, I will sign off, and thank you all for joining, and I'll send it out for 2 weeks in a few days.
Very good. Thanks.